Introduction to Linear Programming. Thank you very much for attending this session. Today I'm going to introduce you to linear programming by using a prototype example from Hillier and Lieberman's famous book, Introduction to Operations Research. We have two products, product 1 and product 2, and they use 3 resources. Contribution margin, what is remain for us after recovering from variable costs, is $300 for the first product and $500 for the second product. The first product needs 1 unit of resource 1 and 3 units of resource 3. Product 2 needs 2 units of resource 2 and 2 units of resource 3. We have 4 units of resource 1, 12 units of resource 2, and 18 units of resource 3. What product mix maximizes our profit given this contribution margins and the constraints that we do have on our resources? You may start solving this problem and try to find out what combination of product 1 and product 2 is the best combination to maximize the profit. But rather than finding the solution, we want to first formulate the problem. What do we mean by formulate? We mean to translate a narrative into a mathematical representation, and we will go through it together. After formulating the problem, after translating a narrative into a mathematical representation, then we translate that mathematical representation into an Excel representation, and then we solve the problem. So we are looking for a general purpose approach to be able to solve all kinds of problems which are similar to this one. We produce some products, we conduct some activities, and then we need some resources, and we have some constraints on those resources, and we make some profit on each product. A general problem which is also referred to as product mix problem. The first thing we need to do is to define our decision variables. What is the decision we want to make? The decision is to know how many units of product 1 and how many units of product 2 should we produce to maximize our profit under the given constraints. Therefore, we define X1 as volume of production of product 1 and X2 as volume of production of product 2. And in this course, we assume production is equal to sales. Now we need to write our objective function. For each unit of product 1, I make $300. So if I'm producing 1 unit, I make 300. If I produce 2 units, I make 300 multiplied by 2. If I produce X1 unit, that is 300 times X1. For product 2, I make $500. And if I'm making X2 units of product 2, I make 500 X2. And I should add these two together. Objective function Z is equal to 300 X1 plus 500 X2. For each unit of product 1, I need 1 unit of resource 1. And I have a total of 4 units of resource 1. So if for 1 unit I need 1, for X1 unit I need 1 times X1, and I don't need to write this one. And this should be less than or equal to 4. This is constraint 1 related to resource 1. Regarding resource 2, for each unit of product 2, I need 2 units of resource 2. for X2 units of product 2, I need 2 times X2, which should be less than or equal to 12. Constant related to resource 1, constant related to resource 2, and for resource 3, for each unit of product 1, I need 3 units of resource 3, and for each unit of product 2, I need 2 units of resource 3. So if I'm producing X1 unit of product 1 and X2 units of product 2, that is what I need, and what I have is 18. What I need should be less than or equal to what I have. And that is resource 3, constraint associated with resource 3. And I cannot produce negative product 1 and negative product 2. So X1 and X2 should be greater than or equal to 0. And that is our formulation. Now I go to solver to solve this problem. Resource 1, resource 2, resource 3. This is product 1, this is product 2. This is left-hand side, this is right-hand side. Right-hand side, resource 1 is 4, resource 2 is 12, and resource 3 is 80. For each unit of product 1, I need 1 unit of resource 1 and 3 units of resource 3. For each unit of product 2, I need 2 units of resource 2 and 2 units of resource 3. Profit that I make for product 1 is 300 and profit for product 2 is 500. If this is X1 and this is X2, these are 2 cells that I assume for my decision variables, I should write this one multiplied by this one plus this one multiplied by this one is what I need. And I type equal to this one multiplied by this one plus this one multiplied by this one is what I need for this constraint. Then I come down here, I type equal to this one multiplied by this one plus this one multiplied by this one is what I need for resource 2, and I come here and type equal to this one multiplied by this one plus this one multiplied by this one. This is what I need from resource 3, and my profit is equal to this one multiplied by this one plus this one multiplied by this one, and that is my profit. Now if I type here 1 and 1, the profit I make is 1 times 300, 1 times 500, which is 80. The resource that I need here is 1 times 1, which is 1. And the resource that I need here is 1 times 2, which is 2. And for resource 3, 3 times 1 plus 2 times 1 is 500. And what I need should be less than or equal to what I have. Copy this down. But I can make this job a little bit easier. Instead of multiplying these one by one, I can go here and say sum product of this one and this one by one multiplied by this one and this one. And it will give me the same thing. Because I am going to copy this down, and if I copy it here, that second one will go one row down, and I don't want that. I'll go back and I mark B6 and C6, push F4, lock it, and copy down 2, copy down 5, and copy down 802. That's it. If I do 5, that's it. Still, that's good, and I'm making 3,100 profit. If I go and make this one 3, this constraint violates. Left-hand side is not less than or equal right-hand side anymore. So this is infeasible solution. Now, how do I solve this problem? I go to data, I click on solver, and then I ask solver, Mr. Solver, please maximize this. Don't minimize it, maximize it. Maximize this by changing my decision variables, which are here, and then by having this one less than or equal to this one, and by having this one less than or equal to this one, and by having this one less than or equal to this one. Okay. However, when constraints are all of the same nature, they are all less than or equal, I can do this too. Delete. After deleting all, I add this one and this one and this one by one, to be less than or equal to these items. Okay? And then I go and select simplex, solve. The problem is solved, and my best solution is to produce 2 units of product 1 and 6 units of product 2 and make 3,600 profit. No other combination of 2 products can produce this much profit. Let me make it 0 and 0 again. Solver, solve. Okay, and that is the optimal solution. This is our optimal solution. Someone comes to you and tells you, I have 1 additional unit of resource. How much are you willing to pay to this person who can change this 4 to 5 by adding this additional unit? Nothing. Because we assume all you can do have been summarized in this model. And in this model, you have 4 units of resource 1, but you have only consumed 2 units of it. So why you need to make this 4 plus 1? You pay nothing. 0. Shadow price of this resource at current situation is 0. What about resource 2? It was 12. What if we can buy 1 additional unit? For this resource, left-hand side was equal to right-hand side. For all resources where their left-hand side and right-hand side are equal, shadow prices or opportunity cost is greater than 0. Shadow price for this one was 0 because left-hand side was not equal to right-hand side. If we give this problem to solver the same as the previous one, we get this solution, optimal solution, and the profit we make is $3,750, and these are our left-hand sides. The previous profit was $3,600. This is $150 more than the previous profit. Therefore, we are willing to pay up to $150 to purchase 1 additional unit of this resource, to add 1 additional unit to capacity of this resource. And this discussion I have is for small changes. We cannot change 12 suddenly to say 24. We need to talk about vicinity of this 12 to see what is the situation. And don't worry about these decimal points. Linear programming accepts this decimal point. You may assume if you produce 2 days, then we have produced 16 units of this product. And if we produce 3 days, then we have produced 5 units of this product. Linear programming allows these decimal points. There are another category of problems which are integer programs or binary integer programs where they allow only integer values or only 0, 1 values. Either you make this company or you don't, 0 or 1. We cannot have something between them, but the linear programming problems that we discuss in this course, decimal points are fine. What if we change the previous 18 to 19? In this case, this is our product mix, this is our left-hand side, and this is our profit. In this case, we are willing to pay up to $100 for one additional unit of resource 3. Let me explain a couple of characteristics of linear programs. We said decimal points are fine. In linear programming, all the relationships are linear. That means a constant multiplied by a variable, like 2x1. No square, no square root, no power, no logarithm. Deterministic. We assume we know all parameters, consumption rates and profit rates. Multiplicativity. If 1 unit of a product requires 2 units of a resource, then x1 unit of that product requires 2 x1 units of that resource. No economy of scale. Additivity. If x1 unit of product 1 requires 2x1 of a resource, and x2 units of product 2 requires 3x2 units of that resource, these two products together require 2x1 plus 3x2 of that resource. Linear, deterministic, multiplicativity, and additive. If we produce 3 products, any combination of numbers that we put in front of those 3, x1, x2, and x3, is a solution. Then we have feasible solution. Feasible solution is a solution which satisfies all constraints. Then we have optimal solution. Optimal solution is the best feasible solution. If you are maximizing the objective function, that is the largest value. If we're minimizing the objective function, that is the smallest value, optimal value. Look at this problem. Objective function, functional constraints, non-negativity constraints. Consider the situation with each of these solutions. Which one of them is feasible, and among feasible solutions, which one is optimal or could be optimal. The first one is infeasible because it violates this constraint. If you put 4 here and 4 here, it will be greater than 80. This one is infeasible because it violates non-negativity. We cannot have negative production of one product to benefit and produce more units of the other product. Third solution is feasible. It satisfies all 3 constraints, and if we put it into the objective function, we get a value of 29. This one is infeasible because 2 times 7 is 14, and 14 is not less than 12. Either this solution is optimal or this solution. Let's put this one over there. 2 is less than or equal to 4. 2 times 6 is 12, and it's less than or equal to 12. 2 times 3 is 6, and 6 times 2 is 12, and that is less than or equal to 18. So this solution is also feasible. Let's see, this one is optimal or this one. If I put 2 here, that would be 6, and if I put 6 here, that would be 30. 36 is feasible and is greater than this one, and the objective function is to maximize, so it's optimal solution. Thank you very much for attending this session. Please make sure to watch my next lecture on this topic.